Good morning, dear student. In previous lecture, we already discussed the ionic method to determine the electron count in given organometallic complex. So in previous lecture, we already discussed how to find out the formal charge on the ligand, and with the help of this, we can easily find out the electron count in given organometallic complexes. So whenever we consider the ionic method to find out the electron count, you should keep in mind that whenever we use ionic method, there should be heterolytic cleavages occur between and the bond. The heterolytic cleavages occur between the bond of carbon and metal atom. So heterolytic cleavages occur again. Whenever we consider a cyclopentadienyl ligand, if you see these three examples, in which the first one is whose hapticity is 1, second is hapticity is 3, and the third one is hapticity is 5. But if you see the formal charge on this ligand, either it is in eta 1, eta 3, eta 5, its formal charge is always -1. So you should keep in mind there is no effect of this hapticity on the formal charge on the ligands. No doubt. Its electron donation is whatever its hapticity. If it is here eta 1, then it's only contribute only 1 electron. Its hapticity is 3, then it contribute 3 electrons, and its hapticity is 5, then it contribute 5 electrons. But the charge is remains -1 whenever we consider it is eta 1, eta 3, or eta 5. So there is no effect of hapticity on the formal charge of the ligand. So let us discuss some examples of this method, electron count by ionic methods. So first find out the formal charge. So the first example is eta 5 C5H5. This is your first complex, eta 5 C5H5 FeCO twice Cl. So this is your example. Organometallic complex is given eta 5 C5H5 FeCO/2 Cl. So if you draw the structure of this complex, then it is Fe, then it having this eta 5 C5H5 ligand is there, then it having 2 carbonyl there, 2 carbonyl also there, and this is your 1 chlorine is there. So this is the structure. So eta 5 C5H5 FeCO/2 Cl. And if you find out the electron count, so first find out the formal charge on the ligand. So we know that this carbonyl, it is our neutral ligands. Carbonyl, it is our neutral ligands. So no charge on this carbonyl. So these are the neutral ligands. Carbonyl is neutral ligand. We know that this chlorine, it is more electronegative as compared to this metal atom, so it have a -1 charge. So if you consider it having a -1 charge, and if you consider whenever there is a whenever we use ionic method, then there is a heterolytic cleavage, and this bond will shift like this. So both the electron goes to this chlorine atom, not both the electron will remain present on this chlorine atom. So it should have a -1 charge. So if you consider this is your Cl, it having -1 charge, and its contribution is 2 electrons. So 1 negative charge means it is 2 electron. Similarly, this eta 5 C5H5, it's also undergo heterolytic cleavage, and it also having -1 charge. So it also having a -1 charge. So both these eta 5 C5H5 having -1 charge, and this chlorine, it is also having -1 charge. And if you find out the electron count, so due to this -1 charge, this Fe, it is in +2 oxidation state. So you should remember. So this cyclopentadienyl having -1 charge, this chlorine having -1 charge. So overall charge on the metal is in the oxidation state of metal is +2. So if you find out the electrons, so we know that Fe, its atomic number is 26. So its configuration is 4s2 3d6. So whenever Fe it is in +2 oxidation state, Fe it is in +2 oxidation state, then it is 4s0 3d6. So Fe in +2 contribute only 6 electrons. Again, if you see this carbonyl, it is your neutral ligand. Its contribution is 2, but there is a total 2 carbonyls. So 2 into 2, total we get 4 electrons. So both carbonyl contribute 4 electrons. Again, this chlorine having negative charge, so it contribute 2 electron. And again, this eta 5 C5H5, it is also a negative charge, so it contribute 6 electrons. So its maximum hapticity is 5, and it also having a -1 charge, and therefore the total contribution, it is a 6 electron. So if you count the total electron, then the 6 electron from this metal atom, 4 electrons from this 2 carbonyl, 2 electrons from this chlorine, and 6 electrons from this eta 5 C5H5 cyclopentadienyl ligand. So if you count this total electron, then it becomes 6 plus 4 10, 10 plus 2, that is 12, and 12 plus 6, that we get 18 electron species. So total this is your 18 electron species. So this is the complex eta 5 C5H5 FeCO by twice Cl. So in this method, in this example, we select an ionic method to determine the electron count. Whenever there is ionic method, then there should be a heterolytic cleavage should be occur between the bond between metal atom and the ligand which is attached to the metal atom. So if you consider in these complexes, the carbonyl is your neutral ligand, but the chlorine and cyclopentadienyl, so chlorine and carbon is more electronegative as compared to the metal atom. There should be a heterolytic cleavage, and there should be -1 charge on this ligands, and therefore it contribute the Cl minus contribute 2 electrons, and this eta 5 C5H5 contribute 6 electrons. And due to this negative charge, the metal atom is in +2 oxidation state, and therefore it contribute only 6 electrons. So 6 electron from Fe, 4 from carbonyl, 2 from chlorine atom, and 6 from eta 5 C5H5 negative. So total 18 electron species is there. Let us discuss the another example of this method or determine the electron count, that is ClMn CO by 5. So it is very simple, ClMn CO by 5. So this is your complex. So we know that these carbonyls are neutral ligands, and this chlorine, it is more electronegative as compared to this metal atom, so it having -1 charge. So Mn, it is in +1 oxidation state. So whenever Mn, we know that Mn 4s2 3d5 configuration, but this Mn 4s2 3d5 configuration, Mn having atomic number is 25. Whenever it is in +1, then it is 4s1 3d5, it contribute only 6 electrons. Again, the chlorine so Cl minus, so it contribute 2 electrons, and the remaining carbonyl, 5 carbonyls, so 5 into 2, its contribution is 2 electron, so total 10 electron is there. So 10 plus 2, 12, 12 plus 6, so it becomes 18 electron species. So 6 electrons from metal atom, 2 electrons from chlorine, and 10 electrons from this carbonyl. So total 6 plus 2, 8, 8 plus 10, it is an 18 electron species. 18 electron species. So in this way, we can easily find out the formal charge on the ligand which is attached to the metal atom, and the oxidation state, that is the formal charge on the metal atom, and we can easily count the electron, either to find out the species 18 electron, it obeys 18 electron rule or not. So in this way, we solve different examples. You will try to solve different examples by this method. In the next lecture, we are very much interested in the neutral ligand methods, so we does not considering any charge in case of neutral ligand method, and in that lecture we discuss some of the ligands and their electron contribution in both ionic method as well as neutral ligand methods. So this is all about the ionic method and the examples. We will try to solve maximum examples from the reference books, and in the next lecture we will discuss the neutral ligand methods and some important ligands and their contribution in ionic method as well as neutral ligand method. Thank you.